Hi, and welcome to a new lesson from Easy Chemistry. This is Mr. Kusai, and today we're going to continue what we started last video. Today we're going to continue the VSEPR Model Theory and predicting the molecular geometry and the hybridization. Our objectives for today are to apply the VSEPR model theory rules to predict the geometry of some molecules. These questions are very important for the exams, for the MSAT exam or for the ministry's exam. And also, we need to understand the meaning of dipoles and polar molecules. If you didn't watch the previous video about the VSEPR model theory, I recommend you guys to go and watch it before you proceed and watch this video. In the previous video, we talked about some molecules and we studied their geometry. It depends on only the total number of pairs, whether they are shared pairs and lone pairs. How to apply the VSEPR model theory? We have some rules. The first rule is the first steps actually, is to draw the Lewis structure of the molecule. And we know that the Lewis structure, it's like the dot structure. It represents the valence electrons for each atom. If you remember, what is the most important thing is the central atom, how many lone pairs and how many shared pairs it has. So drawing Lewis structure is the first step. Then we need to count the number of lone pairs on the central atom and the number of atoms bonded to the center atom. That means only the number of atoms. And that's why, for example, yesterday I told you, if you have, for example, C double bond O, we consider this as one bond or a single bond. Also, if we have C triple bond, C, so also we consider it as a single bond. So we need to calculate or count the number of the lone pairs of the central atom as well as the number of atoms bonded to the central atom. Then we need to use the VSEPR model theory to predict the geometry of the molecule. To understand these steps, we need to go through some examples. Use the VSEPR model theory to predict the geometry of the following molecules. This is how the question comes in the exam. For example, if we are talking about ASH3 or OF2, C2H2 or AlCl4 negative. I'm going for now because we're going to have a special video to solve all those problems, but this is only an example how we solve this problem. So let's talk about, for example, B, and the compound is OF2, and we need to predict the geometry of this compound. The first step is to draw Lewis structure. So we're going to draw Lewis structure for the oxygen combined with two fluorine atoms. So for the oxygen from the periodic table, you will find that it has 8 electrons. The atomic number is 8. That is 1s2, 2s2, and 2p4. Or we can write it as 2 in the first energy level and 6 in the second energy level. Now, for the fluorine atom, each fluorine atom, it has 9 atomic number. That means 9 electrons. So it's going to be 2 and 7. Here we have 6 valence electrons for the oxygen. Here we have 7 valence electrons for the fluorine. So I'm going to draw the oxygen as a central atom with 6 valence electrons. 1, 2, 3, 4, 5, 6. And never mind for now, because later on we can draw it after we know the angle or the geometry of the molecule. So you're going to be able to draw it the correct way. For example, we're going to draw it bent, maybe linear, but the shape is bent. So never mind. I write only the Lewis structure now, the dots of the oxygen, as well as for the fluorine, which has 1, 2, 3, 4, 5, 6, and 7. The same thing, I have another fluorine atom with 7 valence electrons, 4, 5, 6, and 7 valence electrons. Now, as you can see from the molecule, it's OF2, and the oxygen, it requires two electrons to implement the octet rule to be more stable. So this electron and this electron will form a bond or a shared bond. And also this electron and this electron will form another shared bond. Leaving the oxygen with 4 electrons, that is 2 lone pairs. Check the lone pairs now. We have this lone pair and these 2 electrons are 1 lone pair, or this is the first lone pair and this is the second lone pair. So now we can have a better idea about this molecule, the geometry of this molecule. First of all, I need to write the total pairs. They came from lone and shared pairs. So the number of lone pairs equals to 2 lone pairs, 1, 2. The number of shared pairs we also have 2 shared pairs. Or just 2. So the total number of pairs, it equals to 1, 2, 3, 4. We add them, so it's going to be 4 pairs. And now we need to use the VSEPR model theory in order to predict the shape of this compound. We have lone pairs and we have shared pairs. That means we have 4 total pairs. The hybridization should be is, because we have 4 pairs, so S, P, P, and P, so it's going to be sp3. And because of those 2 lone pairs, it's not going to be linear anymore. Those pairs will, the lone pairs, will push away the shared pairs, and the shape will be like this, O, F, and another F, so it's going to be bent. And because we have 2 lone pairs, the angle between them is 107.5 degrees. This is how we solve this problem using the VSEPR model theory rules. First rule or first step is to write the electron configuration and then the Lewis structure for the compound. Number 2, find the arrangement of the electron pairs, as you can see, whether they are lone or shared. Then find the arrangement of the bonding pairs and the lone pairs. Also determine the geometry based on the bonding pairs, which is bent in this case. Of course, here we have 1, 2, 1, 2, and then we have here 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. This is how we predict. I want you guys to try the C2H2 and ASH3 and then D, which is AlCl4 negative sign. This one, it's a negative electron. All right. What do you mean by a dipole? For the dipole, now we're going to understand the idea about the dipole, what is meant by a dipole. Later on, we're going to solve some examples in next videos. So, what is a dipole? A dipole is a product of the magnitude of the charge, which is Q, and the distance between the centers of the positive and negative charges, which is R, the distance. And we give it the letter, the Romanian letter, which equals to Q multiplied by R, where the R is the charge and the Q is the charge and the R is the distance between the charges, as you can see. This is R. And the Q is the charges of the positive and negative charges. And the unit, we call it debye. And 1 debye, it equals to 3.36 times 10 to the power of negative 30 centimeter. So mathematically, dipole moment, mu, it equals to the charge multiplied by the distance, and it's measured in the dBA units, which is denoted by d. All right. Now, what is the dipole moments? What do you mean by dipole moments? Let's check here. For example, if you check some dipoles, dipole, it means that one of the pole has negative sign and the other one has positive sign. Or one of them, for example, this is the molecule. This section, for example, it's partially negative. It means that the electrons are closer to this section. Therefore, this section is partially positive. That means leaving it, the electrons will be away from this part. As simple as this. So let's check. The partial negative, if you put this dipole, as you can see, this is the dipole, and here we have positive, and here we have negative. This is a dipole. If you put it in the magnetic field or electricity, the partial negative end will go to the positive magnet. As you can see, this is the negative. It's going to the positive. This is the negative. It's going to the positive. And also, the partial positive, it will go to the negative pole. So this is the negative and this is the positive here. Also, the partial positive and negative ends are attracted to each other. For example, if you check here, negative is attracted to the positive from the second molecule. This is what a dipole is. Now, we have here the periodic table because we need to use the periodic table in order to understand what is a dipole. For example, these are the electron negativities of the elements. And as you can see, the fluorine here, it has the highest electronegativity. But what do you mean by electronegativity? We will check that in when you revise the video, the covalent bonds. So anyways, the electronegativity is the ability of the atom to attract the bonding pair. So whenever you have a molecule or a bond, for example, between hydrogen and hydrogen, both of them, they have 2.1 electronegativity. So En for the hydrogen, it equals to 2.1. Let's check the electronegativity difference, or the difference between the electronegativity of the hydrogen. It equals to 2.1 minus 2.1, which equals to 0. And that means this bond between H and H is non-polar, because the electrons, as you can see here, are shared evenly. The strength of the atom to pull the electrons is the same. So the electrons remain in the center, in between the first hydrogen and the second hydrogen atom. Let's check for the chlorine, for example. In the chlorine is the same, Cl2. And here, because we have Cl2, electronegativity for the first chlorine is 3.0, and for the second one is 3.0. So the difference between the electronegativity is 0, and this one is non-polar because the electrons are shared evenly between the two chlorine atoms. So whenever we have a di molecule, which means a molecule that consists of two exactly same atoms like H2, O2, N2, those bonds are non-polar. And the reason behind this is why they are non-polar, because the electrons, the shared electrons, are shared evenly between the atoms. For example, nitrogen in the center, oxygen, sorry, it's going to be in the center here. Oxygen is in the center, fluorine in the center, etc. Bromine, iodine, chlorine. And those are the non-polar bonds, when the electrons are shared evenly and when the electronegativity difference between the two atoms equals to 0. What if the atoms now are bonded together? For example, if we have chlorine and chlorine, it's shared evenly, non-polar. Chlorine and hydrogen shared not evenly. And let's check from the periodic table. If we check the atomic, Electron electronegativity for the chlorine, you will find it is 3. Compare it with the H, so you will find it's different. It's not the same. The chlorine has higher electronegativity, so delta En equals to 3 minus 2.1, which equals to 0.9. That means the bond is polar covalent bond. It's polar because of this difference. So that's why the chlorine can attract the electron bonds more or stronger than the hydrogen. That's why the electrons are closer to the chlorine more than the hydrogen. Now, how can we write this? As you can see here, this is the chlorine and this is the hydrogen. This is Cl and this is the H, and this is the electrons, the bonding electrons between them. They are closer to the chlorine. And we all know that the chlorine has, the electron has negative charge. So when they are closer to the chlorine, those negative, this part or this section of the molecule will become more negative. That's why we write it's partially negative with the letter sigma. Sigma, it means partially, not completely negative, because it's not ionic compound. Look at the ionic compound. The electron from the sodium completely transfer to the chlorine atom to become chloride ion. But here, no, it's just like a covalent bond, but it's a polar covalent bond. And the reason why it's polar, because the chlorine has higher electronegativity, the ability to attract these electrons is higher, and that's why we have here negative, partially negative, leaving the hydrogen partially positive. Look, see where the electrons density is higher, it's on this section. Very good. Let's have example about the polarities and polar and non-polar molecules. Our example is about the NH3 and NH3 and NF3. As you can see here, we write these arrows. It means that the head of the arrow indicates or go towards the atom with high electronegativity. We know that hydrogen is lower than nitrogen, which is lower than the highest electronegative atom in the periodic table, which is the fluorine. And that's why the arrow is from the hydrogen to the nitrogen and from nitrogen to the electrons. And as you can see, this is the result of the moment. Let's check, for example, the NF3 now. The electrons or the arrows are from nitrogen to the fluorine, from nitrogen to the fluorine, from nitrogen to the fluorine, and from nitrogen to the lone pair. Always the arrow indicates the lone pairs. But here are the difference between these two arrows, because the nitrogen has lower electronegativity than the fluorine. That's why the arrow goes this direction. And the nitrogen has higher electronegativity than the hydrogen. That's why it goes to this direction. And this is the difference between the two molecules. This is NX3 and this is NH3. All right. Let's do this example. Predict whether each of the following molecule has a dipole moment. Now here we are talking about molecules, not the bond. Of course, BrCl2, if you check here, Br is 2.8. And the Cl is a 3, so 3 minus 2.8, it equals to 0.2. It has some polarity, weak polarity, but it still has a dipole moment. Now, let's check here. In the BrCl2, I'm going to write Br, so this is for A, Br, and I need to check how many valence electrons it has. Br has four valence electrons. 5. So it's going to be 2, and 3. Actually 4. I'm not sure. I need to double check for the for the compound, because the compound I don't think it's correct. So let's take for example BF3. So the boron, it has 5 valence electrons. That means that the Br has 4. Yes. So Br, I'm going to write the electron configuration for Br with 4 electrons. So it's going to be 2 and 2. I have 2 valence electrons and I need 2 bonds. So it's going to be single bond with Cl and single bond with Cl. No lone pairs. So shared pairs are 2, lone are 0, and total is 2. And that means the hybrid orbitals equals to sp, and therefore the geometry is linear because no lone pairs to push these shared pairs. Now, this one is polar. This one is polar. But they are equal because here we have Cl and here we have Cl. The polarity, it's from Br to C. Which one has higher? Let's check. The chlorine, of course, has higher electronegativity than the bromine. So this is the arrows, and this is the arrows, and they cancel each other. That's why the molecule, the overall molecule, is non-polar. Another example of a nonpolar molecule, for example, CH4 is a nonpolar molecule because although this is a polar bond, but all of them are polar bonds and they cancel each other because they are equal. So also CH4 is non-polar. What we need to take from this lesson, how to apply the VSEPR model theory in order to find the geometry of the shape, or the geometry of the molecule, I mean, and what is the dipole moments, how we calculate it, understand what is the dipole moment and the electronegativity, what is a nonpolar bond and a polar bond, and how it affects the geometry of the molecule. I hope you guys learned something new today. If you have any question or inquiry, you can leave it in the comments. I will read all the comments. Also, guys, if you want me to focus on a specific topic, for example, just hit it in the comment. I will check what I can do for you. Have a nice day. Bye-bye.